Okay, welcome to the next class on variational methods for computer vision. Last time we left off with optical flow estimation and the two classical approaches in this field, the Lucas-Kanade approach and the Horn and Schunck approach. As I said, they're very different in the sense that one actually estimates discrete flow vectors for every pixel by assuming that the flow is constant in a certain vicinity around the pixel, and this flow vector is actually estimated one by one for each pixel, whereas the Horn and Schunck is an approach that estimates flow simultaneously for all pixels. And so in some sense this idea that the information, the flow at one pixel, the estimate of the flow at some pixel is related to estimates of the flow in the neighboring pixels is taken into account somewhat more properly in this variational framework. Both approaches were very influential. Both appeared in the same year, in 1981. And we saw that some of the advantages, the Lucas-Kanade is faster, it's simpler, it gives fairly robust results, and it runs quickly even on cheap hardware. And so it's still very popular in certain applications today. The Horn and Schunck, on the other hand, generates more dense flow fields. It's more general. We will actually see extensions of the Horn and Schunck today, which show you how you can generalize from this very classical framework to more powerful, more performant flow estimation techniques. It allows a very nice mathematical analysis once you linearize the flow constraint, and then you have a cost function that is convex. So this Horn and Schunck cost function is actually convex, and so you have existence of solutions, etc., that you can prove. Also, there is this global fill-in effect through the variational setting, through this regularity term that we have in the Horn and Schunck. I'll go back so you see it. Here is the Horn and Schunck cost function, and once this is the linearized flow constraint with the square, it's actually then quadratic in the flow vector, and these terms are also quadratic, the regularizer. So it's a quadratic data term with a quadratic smoothness term, and this smoothness term, as you may remember, in the Euler-Lagrange equation, the Laplace operator pops up, the second derivative operator, and that gives the diffusion that creates this fill-in effect. And this is a nice effect. It basically means that in structures where we have no brightness variations, where locally we cannot associate velocity, we can still propagate velocity information into that area through this diffusion process. And so the flow estimate from some locations will be diffused into other locations where I have no brightness variation. And so ideally, even if I have a black square moving on white ground, which is what happened in the 1980s and 70s, where I can, strictly speaking, only localize or determine the velocity reliably in a corner, that information is then propagated into the interior and exterior through the smoothness term. There are further extensions, and this is what we'll be talking about today. And to start off, let's look at what are the limitations from a, say, today perspective, some 30 or more years after the original publication. We can revisit the Horn and Schunck approach and say what are the drawbacks of both of these approaches, the Horn and Schunck and the Lucas-Kanade. First of all, they typically only work for small motion. Strictly speaking, we want to enforce that the brightness of the first image at x should be the same as the brightness of the second image at x plus v of x. If we assume this velocity is small, so we assume that structures did not move too much from one time to the next, then we can do a Taylor expansion here, which means we take I2 of x plus v and approximate it as I2 of x plus the displacement V transposed the gradient of I2, plus expressions of order V2 squared. So that would be the Taylor expansion. Once I add this error term, I can actually say this is exact. And if you drop the second order terms here and just use this first order expansion and plug that in here, what you get is the optic flow constraint. Essentially, you get I1 minus I2 minus V transpose nabla I2 equals 0. And that we can say is the negative time derivative di by dt discretized. And so we say this is equivalent to saying, sorry, the time derivative plus V transpose the spatial derivative applied to the second image is 0. And this is essentially what we call the linearized optical flow constraint, or the differential optical flow constraint. And that's what's used in Horn and Schunck as a data term, penalized quadratically. And of course, this expression only holds on the assumption that the quadratic terms in velocity are negligible. In other words, it only holds for small velocity. So this is the small v assumption. So it's not just that we assume brightness constancy, but in addition we have to assume small velocities, and of course whether that's a good assumption depends on what you're doing. So if you really have fast motion, then the Horn and Schunck approach in this linearized framework will not work. This is one major drawback, because small motion, what does that mean? Small is a vague term, of course. In practice, it means it should be no more than about 1 pixel. And I mean, when do you ever observe motion that is no more than 1 pixel? Let's be honest, typically you want faster motion. And so these estimators are not going to work for fast motion. The brightness constancy is an assumption that also is not always valid. I mentioned that last time, that if you put into correspondence, say, images of different modality, then the constancy is not fulfilled. Then the quadratic smoothness term of the Horn and Schunck is not very suitable to model discontinuous motion fields. And in practice, that actually does happen. For example, if I move in front of the camera, then the hand moves with a certain velocity. The background does not move. And so in the transition from hand to background, there is a very sudden change in the motion. How to capture these sudden changes is a challenge, and so one of the most dominant things you see in state-of-the-art motion estimation techniques is that, first of all, they can capture large motion, and secondly, they tend to also allow for sharper discontinuities. If we go back to the examples of the Horn and Schunck, right, here's the car, there's the roof. At the end of the car, there must be a sharp transition from moving to not moving. And what do we have here? It's a complete blur, right? So you can't really see where is the end of the moving object. And so this kind of flow estimation is not very useful to, for example, segment the moving objects and extract them from the background. You can't really tell where they end. Sometimes you can, you know, here the back of the car is somewhat visible, but everything is kind of blurred. And that's because of the quadratic smoothness penalizer. It just doesn't allow discontinuities. They're penalized quadratically. And so you already know what's going to come next. Of course, non-quadratic penalizers. So there's actually, I said Horn and Schunck has been cited thousands of times. I mentioned the exact number of citations. Here it is. No. I think I had it in the beginning of the I'm sorry about that. Somewhere I had the citation number. 8,900 citations in January of this year. So around 9,000 citations. The numbers tend to go up fairly quickly with high cited papers. And so, of course, all of these papers build up on the horn and chunk, and many of them just apply it in some application of motion estimation, for example, to estimate fluid flows and understand the motion of fluids from videos, or to estimate plant growth. This is an important application if you want to know a leaf of a plant, where does it tend to grow most, where does it grow less. You can actually take images of the leaf over time while it's growing, and then you can estimate the growth using these algorithms. You can determine where is the displacement happening. So these are all applications, but a lot of these 9,000 papers actually improve on the horn and chunk. They say this is the standard approach, and this is where we go beyond. This is how we suggest to make it better. And now, not surprisingly, in this lecture, I cannot really tell you all of these approaches and mention everything that has been done, but I decided to mention at least a couple of advances in this field. And which advances to mention is a bit of a random selection, but I've decided to mention those approaches which still stick to the original horn and chunk framework, and that extend it in a somewhat straightforward way and in a way that actually boosts the performance. The first paper I decided to mention is a paper of Brox et al. That integrates some components. Not all of these components were novel at the time of publication. Some of them had appeared over the years after the horn and chunk approach, but it nicely kind of summarizes a number of advances in this field. The first contribution or advance that people made in this field is to move from quadratic penalizers that tend to over-smooth, in particular motion boundaries, boundaries between objects and background, and replace it with a non-quadratic penalizer. Of course, there are tons of possibilities for non-quadratic penalizers, and indeed many of them have been suggested. This is one of the simplest non-quadratic ones, namely the total variation. But here again, this is actually a little bit simplified. As you know, the velocity is a vector. It has two components, v1 and v2. And so what we mean here is not the divergence, but what is meant is, and in fact there is a degree of freedom here. One solution would be to do v1 and the norm of v2 dx. A shortcoming of this formulation is that it's not rotationally invariant, because you're separately penalizing the velocity in x and in y direction. And so if you take a different coordinate system, that regularizer, at least in this formulation, will change. And so you can do other approaches. You can take nabla v1 squared plus nabla v2 squared, and then the square root of that dx, right? That's an alternative. So when I say the norm here, you know, anyone who reads this would, of course, first ask, what exactly do you mean by this expression? Do you mean this, or do you mean this, or do you mean something else? Now you would say, okay, then maybe we should use this one. It's rotationally invariant. It doesn't depend on the choice of coordinate system. Still, some people use this one because it's much simpler to implement. So there are trade-offs here, and they affect the speed of computation, etc. And so all of this has been done in many, many ways. And so I'm not going to really detail everything. But the key is that you drop the square, that you somehow get a penalty that doesn't grow quadratically with the gradient, but just linearly. Of course, you could also go to even less than linear and say at some point, I don't want to right? What we have here is, if this is the gradient of the velocity, the original horn and chunk looks like that. It grows quadratically. This new total variation type regularity grows linearly, the next better thing in terms of modeling might be to say, well, we want smooth velocity fields, but at a boundary of an object, the velocity may change discontinuously. And we want a velocity that can really jump, in the sense that the gradient can really be infinite even at that location. How can we do that? Well, one thing is we can take, for example, what's called a truncated quadratic penalty. That would be this. This is in fact related to the horn and chunk, to the Mumford-Cha. The piecewise smooth Mumford-Cha is essentially such a penalty. That can be done. The reason why it's not as popular is because this is not convex anymore. Whereas this total variation type regularity is still convex, meaning at least the regularizer can be minimized globally. The data term is of course not convex, so there is still an issue there. So these are all considerations that people considered, and they proposed various solutions. The Brox et al. Papers uses this total variation type regularizer. In addition, instead of using the linearized data term, they actually used the original nonlinear data term. And more specifically, even in the data term, they favor a non-quadratic data term. And so this is a common strategy to go both in the regularity, you move from quadratic to non-quadratic, and in the data term you move from quadratic to non-quadratic. Why do you do that? Well, to account for errors in the brightness constancy assumption. Sometimes brightnesses do change due to lighting variations, but also due to specularities and all sorts of things. And if you want to be, or for example, something that happens a lot in optical flow is that you have occlusions. That, for example, one object moves behind the other, and then the corresponding point, even if it's the right partner, it's not actually visible, it's occluded, and so that brightness here will not be visible in the other image. If you take a quadratic data term, it will say, no, this is not a good correspondence because the brightnesses are very different. And so it will disfavor that kind of solution, whereas if you drop the square, you say, okay, it's not a good correspondence, but you know, don't pay too much for it. And so that tends to improve the performance as well, to make the algorithm more robust to outliers. And lastly, they suggest to also use the gradient constancy to account for the fact that sometimes the brightness is not preserved, but maybe at least the local brightness variation. The gradient of the intensity is an expression that doesn't depend on the absolute brightness. And so in summary, what they suggest is again a variational approach with a data term and a smoothness term weighted here by alpha. I call this lambda before, it doesn't really matter. Some typically positive constant alpha. The data term, as I said, is the brightness constancy, and you see it here, the gradient constancy. And that is then, there are many ways to write this up, but this is one fairly elegant way, and that is to say we take the quadratic data terms and then we apply a robust function psi, which is nothing but the square root really. The reason why they add a little epsilon here and don't take the exact square root is they want to make things differentiable. And so that means they take this black solution here, but at the 0 point they basically smooth it off a little bit. And so that is the norm of the square root of x squared plus epsilon, if this is x here. That's what it looks like. So for large x it's just the norm, and for small x it goes down to epsilon, or if you put, yeah. So that makes it differentiable, which means we can compute gradients. You don't have to do that. In fact, more recent approaches do not use that approximation, and they rather use what we discussed about these primal dual algorithms, which allow to model sharp transitions and these discontinuities. Here's the smoothness, the regularizer, and what they use here is they want to apply this to an entire video, and so they take not just the spatial gradient but also the temporal gradient. Actually, this is pretty much exactly what the horn and shunt is. If you look at it, this oh, sorry, no. So what they assume is that the velocity is not just smooth in space, but also in time, that from one time instance to the next, the velocity at a given pixel is likely to be similar, not the same, but similar. And so you get in a spatial smoothness and a temporal smoothness. As I said, some of these ideas had been around before, and so this paper of Brox and co-workers summarizes all of these. And it led to what was at the time the best performing optical flow algorithm. And so putting this non-quadratic data term with the non-quadratic penalty term, smoothness term, see, we take the same square root here and apply it to the smoothness regularizer. U and W are the two components of the flow vector. So V consists of U and W, and then the third component is 1 here, to integrate it into this framework. And so this, what you have here, the x is actually x, y, and t, so you're integrating this over x, over y, and over t, so over time. Which means essentially you're estimating not just one flow field, but a whole family of flow fields for all time steps, say for a video. And here's the result applied to the exact same example that I showed before for the Lucas Canade and for the horn and shunt. Here you see the flow field. And what is characteristic about more recent flow estimators is that they tend to nicely preserve discontinuities, as you see here. So you can more clearly see there's some object moving here, and at some point you get into the background, you have fairly sharp transitions between object and background. Another effect actually of this non-quadratic smoothness term that allows these sharper boundaries is that we tend to see that the flow is not underestimated. So if we compare, for example, the horn and shunt here and this extended variant of it, of Brox and co-workers, you see that the region here, the moving region, has a much stronger brightness than in the horn and shunt. And that is because the background, remember, is not moving here. And so with the smoothness constraint, that constant background motion will be propagated to some extent to the object as well. And that leads to a systematic underestimation of the magnitude of the motion. Whereas here the motion, the magnitudes are estimated more correctly. And so you see, all of a sudden we get a much better flow estimate, better in terms of the direction of motion. Here everything is green, so the car is actually moving to the left, as you would expect. And the tram is moving to the right, again as expected, whereas here you have some spurious incorrect motion estimates. And we have, in contrast to horn and shunt, much sharper boundaries of the motion. And so this is what I mentioned last time already, that at the start the Lucas Canade seemed to be better in terms of performance, but on the long run the horn and shunt approach allows for generalizations that ultimately outperform the Lucas Canade. And so not surprisingly, all state-of-the-art optical flow algorithms nowadays, we'll see some examples in a second, they are built on this architecture of horn and shunt. All may not be right, but most of them, let's say. because there's such a zoo of algorithms out there today. It's somewhat difficult to generalize here. But so the horn and chunk variational architecture has become extremely influential, and most state-of-the-art methods build up on it. Here's some further advances. So we see Brox et al. Was 2004, so that is now 10 years ago. And so let's go a little more recent at least. So there is this paper of Wedel and co-workers, which is called Adaptive Regularization for, I don't know, flow estimation or something. It was published in the ICCV in 2009. And it adds 2 more improvements over the Brox et al. Work. The first one is, so again, these improvements were not all proposed in this paper. They were proposed slightly earlier in the years before, but it kind of integrates some of these recent developments and shows that this leads to better flow estimation. One approach it integrates is a quadratic regularizer, a quadratic relaxation, which decouples the data term and the smoothness term. Here again is the data term and the smoothness term written in a slightly simpler form, so not the square roots and not the epsilon, but really just the data term norm and the total variation regularizer on the flow. If you look at this cost function, one of the difficulties in terms of optimization is it's not convex. The smoothness term is convex, but the data term is not, because V is inside the argument. What you can do though is you can add an auxiliary variable, U, which basically decouples the data term and the smoothness term. And these decoupling strategies are extremely popular in optimization. This is called a quadratic decoupling because you couple U and V quadratically. In other words, you have a parameter theta here. Now imagine theta goes to 0. If theta goes to 0, that weight will become higher and higher. It will become stronger and stronger, and it will impose that U and V should essentially be the same. Otherwise, the cost grows enormously. We're now optimizing over V and U, so we have actually not one velocity field, but 2. And the idea is that we have a velocity V, field V, that matches the brightness. Oh, sorry, it should say I1 and I2 here. It just says I here. So this is I1, I2, I1, I2. I dropped that. So this is the 2 images, I1 and I2, and V should be such that the brightnesses are matched of the 2 images, and U should be such that it is smooth, so U should be smooth. And the third term here, this coupling term, it says U and V should be the same. Now you would say, well, what's the difference? You know, if U and V are the same, then I really have the same expression. Indeed, for theta going to 0, basically the 2 expressions are the same, because then U must be equal to V, and then I have the same here. But the nice thing about this decoupled cost function is that it's much easier to minimize. The reason is that as a function of U, let's look at the optimization in view. In U, this is a simple convex problem, because this is quadratic in U, and there's the total variation. In fact, this is called the Rudin-Osher-Fatemi model. Quadratic data term and total variation penalty. So that, and there is tons of algorithms that minimize this globally and efficiently. So this is really fast and easy to minimize optimally. In V, we have that term here and this term here. There is no smoothness term in V because that's in U, not in V. And so this is not convex in V because V is in the argument of the brightness function. But this is a problem in V that can be solved pointwise. Why? Because the optimal solution for V for any pixel does not depend on the solution for the other pixels. Because what we have here is v of x here and v of x here. We are summing over x, but the solution for v at one x doesn't depend on the solution at another x. They're completely decoupled. The only reason that there is a coupling is through the smoothness term, but there's no smoothness in v. And so for fixed u, the optimization in v can be solved pointwise. I can just for each pixel search the best value of v. And that can be done quickly. In particular, you can use the GPU to find the best v for all pixels in parallel, because the best v for every pixel doesn't depend on the v's for the other pixel. And so the optimization in v can also be solved globally. And so this is interesting because we start from a non-convex, difficult to optimize problem, and by this decoupling we end up with two problems, one in v and one in u. Both of these problems can be solved globally. So I can find the globally best u for a given v, and I can find the best v for a given u. Nevertheless, this alternation of two globally optimal steps will not lead you to the provable optimum of the original problem. That should be kept in mind. So if you solve an optimization problem by alternating two steps, each of which is provably optimal, I find the best v for a given u and the best u for a given v, it doesn't mean I find the global optimum of the joint problem. That's important. Sometimes people overlook that and think, oh wow, that solves the problem. So it doesn't compute the provable optimum of the original problem, but it basically makes the problem much easier to minimize. And it works very nicely, actually. The second contribution that is integrated in this Wedel et al. Paper of 2009 is that the smoothness term is made adaptive. So rather than taking the norm of nabla v, so the total variation of the velocity field, we take the total variation but weighted with this exponential function here. And what does this exponential function do? Let's look at it. Basically, the contribution is if I have the brightness gradient, so the how strong brightness variations do I have in a certain location, then that function e to the minus gradient, let's just write it, looks like that. So it's a function that has large values if there is no gradient, in fact 1, and the value decays exponentially the stronger the brightness gradient. The consequence of that is that the smoothness is not penalized in locations of strong brightness variation. Because if nabla I is large, so down here, then that weight is very small, and so the velocity smoothness is penalized very little. The effect is, you can imagine, if I have an object moving, typically the moving object will have a different color from the background. And so at the locations of the boundary, there will be a strong gradient, typically, not always. I mean, you can still have the example of a white square moving on a white background, but then, you know, what do you expect to estimate, right? So typically you do see a strong gradient at the edge of the object, and then you say, at that point, I don't want to penalize the smoothness of the flow field, meaning I want to allow the flow field to jump from, say, a large motion of the object to zero motion in the background. And so this is, and the nice thing about this smoothness term is it's adaptive, but it's still convex in V, right? So it allows for very sharp discontinuities in the flow field wherever I have a strong gradient. But as a function of the velocity field, this weighting doesn't affect the problem. It's still a convex problem. It's just a weighted total variation. I said typically the object has different color from the background, and then you would expect a brightness variation. You have to be careful. The drawback that you're buying with this adaptation is the following. Assume that you have a zebra moving. what will you have? With a zebra, you have lots of very strong brightness changes, right? If you have these stripes, right? Then you have lots of very strong brightness changes, and at all of these brightness changes, this regularizer will say the flow field can be discontinuous. It can jump there. And so that filling effect that you want from the regularizer, it will be strongly reduced on the zebra. Wherever you have a transition from white to black, there will be no filling essentially. And so this is a shortcoming. The reason why this still tends to work on average, we tried this and we found it does improve things. The reason is that this benchmark that we tried it on doesn't just have zebras in it. So in some sense what you see in a lot of these approaches here as well is that they are built on assumptions, and the idea is that the assumption typically holds. It doesn't hold all the time, but on average it's a good assumption. And if it is, then on average it will improve the performance. In some examples it might decrease it, but on average it does improve. And the issue is, I mean, it reduces the filling effect in strong gradient locations, but that's, you know, that's not terrible in the sense if there is a little less fill-in here or there, it's okay as long as the boundaries of objects are better preserved. And so there's actually tons of benchmarks for optical flow that have been proposed over 20 years by now. And there is new benchmarks coming up with every year. In fact, there's 2 or 3 more benchmarks that appeared in the last 2 or 3 years. 2 years actually. But this is a benchmark that was used extensively. It's called the Middlebury Benchmark. There is a number of so-called Middlebury benchmarks. They're called Middlebury because they were developed and published at the Middlebury College in the US. And this is the optical flow benchmark. There's also a stereo benchmark. There's also a multi-view benchmark. But this is the optical flow benchmark. And here you see flow algorithms ranked by their performance. This is a review paper. I took this from a review paper of Baker et al., which is on the Middlebury Benchmark site. It was published in IJCV 2011. And the aim of this review paper was kind of to summarize what has been done in the flow literature. And what are the key innovations that appeared over the years, and to what extent do they actually improve the performance. And so this is all discussed extensively in that review paper, and here you see snapshots from that paper. And for example, this adaptive approach of Wedel and co-workers that I mentioned earlier is in this benchmark ranked number 1, so the best performing. And in comparison, for example, you see the horn and chunk is down here. So you would say it's almost the worst performing. And this is not untypical for the development of science, that some paper that innovates the world and creates new ideas, in the end will not be the best performing method. But it will be very influential, and this is kind of the forefather of pretty much all of the above more performant algorithms. Here's the Brox et al. Method that I mentioned, and these are various extensions. We were actually quite involved in optical flow estimation around 2007, 2008, 2009, and so actually Brox was a postdoc with me. These are all approaches, this one, and this one, that we published around 2008 and 2009. And then I should say we stopped working on optical flow. At some point you get bored, of course, of doing the same thing over and over again. And so now I should say this is no longer the state of the art. I haven't really followed up, but there's new algorithms popping up, you know, every couple of months. And so there is a couple of more performant algorithms there today. This is again a snapshot of the Baker et al. Paper, this review paper published in 2011. And here you see they went into a little more detail on what what contributions did which paper contain. And so they list a number of performing papers, including the Horn and Chunk, including the Brox et al., including the Wedel et al. Paper I mentioned. And then they list what do they have. For example, the Horn and Chunk has a quadratic penalizer, whereas, as you can see, most other papers tend to use an L1 norm data term. This is the data term, this is the prior term, this is the optimization. You know, this analysis is in some way a way to structure what has been done before, but as always, you know, in such a structure you cannot incorporate everything. For example, one aspect I think is very important in terms of optimization is this quadratic decoupling. And as you can see, they list things in optimization. They mention continuous gradient methods, continuous variational, whatever, but they don't actually mention that quadratic decoupling. This is what I find important, but it's not actually. So they didn't pick that up as a key innovation here. So there's always a matter of interpretation in the end. At least from our own work, my impression was this was one important innovation, actually. Yes, and so you can study and analyze and compare extensively. As I said, we moved away from optical flow. I found there's other also interesting problems. One thing you notice is when you do flow analysis, typically you're not as much interested in actually estimating the flow accurately at every pixel. This is just one thing you might be interested in, but typically on the long run you want to solve another problem that comes behind it. Right? Typically when I have computer vision types of applications, there's something that I want to do. I don't just want to estimate the flow from one pixel to the next, but I want to see objects, I want to recognize things, I want to extract objects and put them into a different background. Here, for example, you see a video that I recorded. It's just 2 consecutive images, something moves, and what you want is you want to determine what is the moving object. And the challenge is from a segmentation point of view. We talked a lot about segmentation. One of the things you see is that the colors are actually quite similar between the object having a somewhat reddish brownish color, the table as well. There's some brightness variations, but the thing is here is the object is much brighter than the background. Here in turn it's actually much darker than the background. So in other ways it's very hard to say what characterizes the object in terms of its colors and makes it different from the background. And a lot of human psychophysical studies show that what humans use to distinguish objects from their background is not so much the color but the motion. The fact, and you see the hand here as well in the video, you see it very quickly because it moves. Even if it's just a little motion, in this case it's a motion towards the camera. It moves, but you see and you can distinguish the object because the motion is different from the background. Here, this is a somewhat simple case where this camera is static, so the background is not moving, just the object is moving. But you can imagine if you have a moving camera, then everything moves, but it moves differently. If just the object is moving, you can do what's called change detection. You just determine where does the color change. In the background it doesn't change because it's not moving. In the foreground typically you see brightness color variations, and then you can threshold how much change did I see, and you will be able to extract more or less the moving object. But that no longer works, of course, if the background also moves. And then this motion, this problem is called motion segmentation, so segmenting objects based on their motion. If you look at it, it's actually a chicken and egg problem. Chicken and egg in the sense that in order to segment the object based on its motion, I have to know the motion, right? If I know the motion of each pixel, then I can determine, you know, group pixels of similar motion and distinguish them from pixels that have different motion. The problem though is that in order to estimate that motion, I typically need to have information from the environment. In the Lucas Canade, I need to assume that there's a whole region around me that has the same motion. But that I don't know because I don't have the segmentation, right? If you had the segmentation here, let's say someone told you where the object is, you could say for this pixel, I take a window around it that only includes the object, not the background, because I don't want to get misleading information to estimate the motion here. I will aggregate information from an environment that only includes the moving object. But as I said, to get the moving object, you have to have the motion. So there is a certain chicken and egg problem. And one way to tackle these chicken and egg problems is by an optimization approach that solves everything together. And so this is an example that I proposed in 2005, is an approach which I called motion competition. And in fact, it is very much building up on the Mumford-Cha model and on this region competition idea that we saw earlier. And you will actually recognize the structure of it. What I want to estimate is I want to estimate a number of regions, omega 1 through omega n in the image plane, say the hand region, the background region. And I want to estimate the motion vector, a motion vector, say just translational motion, for each of these regions. Let's call them V1 through Vn. And what do? We have a data term, a quadratic data term, like in the Horn and Schunck, with a velocity vector Vi. It's not like in the Horn and Schunck because it's more like in the Lucas Canade. The vector is actually constant. It's not space dependent. So this is a constant vector. The difference is in the Lucas Canade, you assume this velocity for a certain region around the pixel. What do here? We assume this velocity vector for the entire region omega I. So in some sense what we're doing is we're carrying the Lucas Canade idea one step further and say, if you knew exactly the support region for that motion, say the entire hand, then you should actually use this entire support region to estimate that motion. It's going to be extremely robust. You will find one velocity vector to model the whole hand region. And you will find similarly one velocity vector to model the entire background region. And so here you can estimate the best velocity assuming you have the segmentation. And in turn you can actually estimate the segmentation assuming that you have the velocities. And in practice you can do both by alternatingly minimizing the problem. And what we have here is, as in classical segmentations, we say the transition between different regions is penalized. So we penalize the boundary lengths of the foreground and background and the various object regions. And so what we have is actually quite reminiscent of the Mumford-Cha. Maybe to recapitulate for those who don't remember, the Mumford-Cha, the piecewise constant Mumford-Cha, was saying that I have a set of regions, I, then I integrate over the region omega I, and then it was saying approximate the brightness with a constant mu I in that region, and then we had the lengths of the boundary plus nu times the lengths of the boundary of that. That was the Mumford-Cha, and all we do now is replace this data term with the optical flow data term. And so we're saying, don't find regions that have constant color or constant brightness, but find regions that are constant in their motion. So it's actually the exact same idea, but carried to the motion scenario. And whereas here we estimate regions, omega I, and brightness constants for each region, mu I, here we estimate the regions and the motion vectors for each region. Then it turns out, for example, in the sequence I showed you, you have objects moving towards the camera. The translational motion is somewhat simplistic. You can generalize that. You can introduce other types of parametric motion for each region. For example, affine motion that includes rotational flow fields and zooming. If you move towards the camera or away from the camera, you have these divergent flow fields. And this is all included, in such a parametric model. Right, so we have some matrix that is space dependent, S of x, let's call it, and 6 parameters, A1, AI through Fi, that model that motion. For example, if you put A, B, and DE to 0, then you just have translational motions, because then you have 1 times C, Ci, and here 1 times Fi. So actually, let me write that out so you see in what sense this is a parametric motion. The velocity v in region I is modeled as Sx times Pi, and if I multiply this out, then all you get is Aix plus Biy plus Ci, and here I have Dix plus Eiy plus Fi. And so this is the motion model that we have, and so that's a linear motion model in x and y, in the x component, and also linear in the y component. And in particular, if you set these 4 parameters to 0, you just have the translational component. But otherwise, you can have rotation. For example, rotation would be if this matrix defined by AI, EI, BI is a rotation matrix, then you have a 2x2 rotation. So there's a variety of motions that can be modeled in this way, but what's important is that we still have a finite, very small number of parameters, 6 in fact, to model the motion of the entire region. And it allows us to model rotation, so it's a very compact way to represent an entire motion field. And if we use that Vi in the optical flow, here it is, so the gradient times Vi plus It, so that is the linearized flow constraint, except that we now have it parameterized in Pi. So rather than estimating as before a 2D velocity vector, 2 components for each region, we now have 6 components to estimate for each region. That is more parameters to estimate, but what we gain is that we can model rotational and divergent motion. And so we can do more complex motion models. And so in the end, what this generates is a flow field that is piecewise parametric. Right? Piecewise in the sense that we have a set of pieces, puzzle pieces if you will, and parametric in the sense that in each region the flow is constrained to be affine. And the nice thing about these approaches is that they run very fast, so even in 2006 we could show that you can implement it at 30 frames a second. And so in real time it gives you region boundaries and it gives you the motion of each region. Here's some examples. So this is on the flower garden sequence that I showed you earlier. This is actually from the 2005 paper. I was using level set methods at the time, and this is actually the Chan-Wese level set formulation running on this cost function. And here you see this is the initialization. There is 4 phases, a blue, red, yellow, and white phase. And once you minimize this cost functions, what happens in the iterations is the boundaries evolve and the motion models evolve. So we're simultaneously updating the geometry and the motion models. You see that here. In the beginning, the red region has fairly large motion, and with the iterations, the red region is associated with the background, and the background has very small motion, and so upon convergence you have a very small translational velocity in the background, whereas the tree region in the foreground is associated with yellow. And the blue region has medium-sized motion. It's kind of the flower bed here that is not very far back, but not very much front either. And so what it ultimately generates is a partitioning into various depth layers. You can see the tree, the midplane, and the background here. Here's again this divergent motion of the camera moving to the I think this video will not play. So I'll just show you the video. Here you see how the curve evolves and separates this moving background, moving object from the... I slowed it down explicitly to show you this evolution. As I said, it runs much faster in practice. And you see, actually, in this visualization, in this animation, you see how the motion field is being updated while the geometry evolves. So you see that with better object boundaries, also the motion estimate for each region gets improved, all the way to the effect that in the end you have a segmentation of the object, and you have the flow field of this divergent flow field, where you see that this is more or less the center of the motion. Here's, by the way, this flower garden video, where you see as well how the regions evolve. One thing that's actually characteristic about the Chanvese level set formulation, we talked about it, is that it allows boundaries to jump. So one thing you see here is that the red boundary, at some point, a new red region pops up in this area. The next thing I wanted to talk about is sometimes you're not just interested in optical flow, but in really 3D motion. Typically the world we live in is three-dimensional, objects move in 3D. One of the shortcomings, we talked about it, is optical flow only estimates the motion in the image plane. Now you would say, well, that's all I can see, you know, how can I estimate 3D motion if I don't see it in the image? One thing you can do is you can take two cameras. You can take two cameras, and this is what we did in collaboration with Daimler Research. This is a PhD student of mine who worked with Daimler. And so what we did is we put two cameras into a car near the rear view mirror, front facing, and with two cameras you can do depth estimation, so you can get the depths of a scene. And once you film in time, you have a scenario which is a little bit like the optical flow scenario, namely a temporal sequence of images, except I have two images. And so whereas in optical flow you would say we have a time axis and we take images over time. Here's an image, here's the image at the next time step, so time evolves in this way. In the scenario we are looking at, we now have two images, and these take film video, they're synchronized, and so between the two images we can compute a stereo depth map. And then we can compute optical flow here for this camera, optical flow, and same for this camera, optical flow. And we can compute stereo for these cameras as well. And in the end you can do all sorts of things, but when you look at this scenario and you get new images as time evolves, when you look at this scenario you realize it's actually smarter to solve the whole problem jointly. And ideally you would try to estimate 3D geometry and motion of structures. What we did in this setting to accelerate the process is we computed the stereo depth map we were able to do that in real time. And so we got a real-time stereo depth map, and then we estimate motion, but not just in 2D but in 3D. Because if you have a depth value at each time, you can see how does the depth change from one time to the next time. How does the depth map that I compute between the two images, how does it change? And that gives me the change in the depth coordinate. Let's call it d prime here. So we have a disparity associated with the depths, and we have a change in the disparity. So d is the disparity from the left image to the right image, and then you can see, much like in the brightness constancy assumption for optical flow, we can do a number of assumptions for this generalized scenario. The first assumption is that we have an optical flow constraint for the left image, so L represents the left image here, and there is an image at time t and an image at time t plus 1. So this I call IL at time at x, y, and t, and this is IL at x, y, and t plus 1. And so for the left image, we have the optical flow constraint, meaning if I displace by a flow vector with components u and v, so that is x and y component of the flow, then the brightnesses should match from the first image at time t to the second at time t plus 1. And I have a similar constraint for the right image, except that now I am the pixel x in the right image corresponds to a pixel x shifted by that disparity. In stereo, you have a disparity between the left and right image, assuming that the cameras are aligned so that the displacement only happens in the x component. And then there is a disparity, so the corresponding pixel to this one in the right image is that one. And the corresponding pixel to this one in the right image is the same pixel shifted by the flow and shifted by the change in disparity. Because the disparity over time evolves, so the disparity changes by d prime, that is the change in depth, and so the change in disparity, and so you get this correspondence here. This disparity happens with rectified images, as in this setting. We rectify the cameras. It only happens in one of the coordinates, so in x, so there is no disparity in y. And so in y, we just have the same y plus v. And then, in addition, if you can enforce consistency of the left and right images at time t plus 1, so that is consistency here, and that says that the pixel x shifted by the velocity, so this is where it moved at time t plus 1. We are at x plus u and y plus v, and here, in addition, we have that disparity and the change in disparity. And that should be the same brightness there. So we have a brightness constancy assumption between these images and between these images as well. So there is kind of a brightness constancy among all of them, and we try to incorporate that by saying we want some consistent solution. That a disparity d which matches these images, so there is d here, then a flow u and v that matches these and also these, and then a disparity d plus d prime that matches these images. And so overall you get these constancy assumptions, that this should be the same as that, this the same as that, and this here should be the same as that, or the difference should be 0 if you want. And then you can integrate all of these in a variational approach, and this is what we did. So we have a data term, a smoothness term, and the data term now takes 3 components. One is the first constraint for the left image, for the right image, the flow constraint, and then a consistency constraint between the left and right images. And so in some sense what we're doing is we're estimating optical flow for the right camera and flow for the left camera, but under a constraint that left and right should be consistent. And that is this constraint. The issue that you find then is in practice, if you do stereo reconstruction and disparity estimation, you don't actually find a disparity for every pixel. And so what we did to account for that is we masked out those pixels where we don't have a disparity. So we always estimate flow for the left camera, but for the right camera we only impose a data term and this consistency term between right and left if there is a disparity. So there is a masking function C, which essentially is 0 or 1, 0 if there is no disparity, and 1 if we actually have a valid disparity. Yes?
The U and the V always have to be the same for both images?
Yes. That's the whole point, that we have, that we see something moving through these cameras, but the difference between the two cameras is only based on this disparity. And that assumption actually is, I think, a valid, definitely. Because you see something that moves, you see the same motion in two cameras, and the difference is only that it is displaced by this function d, x plus d. And then in this, if the disparity changes over time, then at time t plus 1 we have d plus d prime, the change in disparity. And so d prime is actually the motion in the disparity space. And what we then do is we penalize the smoothness by saying the x and y component of the flow should be smooth and the disparity should also be smooth. The change in disparity should be smooth. So that d prime, which is the velocity due to this in disparity space, should be smooth. So it's almost, and you see we of course take the non-quadratic smoothness terms and the non-quadratic data terms. And then all of this is minimized, and this is what you get out. So here you see the left image at time t and the left image at time t plus 1. What happens here is the car is standing, we're driving down the street, and this pedestrian is walking in front of the camera. And what we show here is we actually computed this, it's called scene flow. In the literature, this is called 3D scene flow. Actually, our colleagues at Daimler went on to call this 6D vision. I think it sounds better, but we call it scene flow because that is actually the established terminology in the community. And so what you have here is we estimate the scene flow for the whole image plane, and this is a zoom in, and what you see is that you get actually fairly accurate motion vectors. And in contrast to standard optical flow, there are two differences. First of all, these vectors live not on the image plane but in 3D space. So we can associate a vector with each point in the 3D world, which is much more important because we actually want to make statements about the 3D world. And this is something one should not forget, that in vision we're not actually so interested in making statements about the image and the image plane, but about the world behind the image. And so we actually have 3D coordinates of points. As you can see here, there's the plane and everything is set on this plane. And so these vectors actually live in 3D. And the second difference to flow is these are 3D vectors. They actually point they're actually vectors in 3D, so in the image plane, and there is a component in the third dimension. Here's another example. Oh, maybe one more comment. This is actually, we were actually surprised at how well this works. Because if you look at this estimates, you see that the algorithm says the pedestrian is walking, It has a medium-sized velocity, but you can clearly distinguish not only that there is a pedestrian walking, but you can even tell that there is an arm moving slightly faster than the mane of the body, and the left leg, sorry, maybe the right, I can't see it from here. I think the left leg is, because it's in front here, the left leg is moving faster than the body, whereas the right leg is standing completely. At that instant, one leg is standing, the body is moving to a certain, so you can actually distinguish even within the pedestrian this motion pattern. You can tell which leg is moving, which leg is fixed to the ground. Is green. Green means static here. So the color code that we used here is that green is static. I should say static actually means static in world coordinates, because I'll show you in a second these sequences were actually filmed from a driving car. So we drive, which means on the image plane everything moves. We have brightness variations everywhere, but we can actually determine the ego motion of the car, and we can subtract that ego motion from the velocity field that we estimate in order to render everything in world coordinates. And this is important for subsequent reasoning. If I want to know, do things move in the world, I don't mean with respect to my camera, I mean do they move in the 3D world. So even if I see motion because I am moving, right, if you move through the world, then colors, you know, move around. But what you want is you want to understand what is moving in world coordinates. And then you see this car is actually not moving, it's completely static, and in this pedestrian the right leg is static, the left leg is moving. Here's other screenshots. I'll show you videos in a second, but these are screenshots taken from these videos. Here again a scenario where you see there's a traffic light which is red. So the car in front is actually standing, it's static, it's all green. The ground is estimated, it's all green as well. The trees are not perfectly green, there seems to be some motion. In fact, here you can see motion. I don't know if there's maybe a car or something back there. But you clearly see that there is a biker who is moving fairly fast. And so you see the biker is almost completely red, which means that it actually estimates the motion of the biker quite accurately. This is just the stereo. Color-coded red means front and green means back. And here, this is a visualization of the 3D scene flow. Let me see if I can find the video. There's tons of videos. I'll just show this one. So what you see here is this is out of the car. This is one of the two images that we get. It shows you a little bit the scene we're filming. We're filming essentially what the driver sees out of the window. And the stereo camera has a baseline that is slightly bigger than the human eyes, but more or less. So this stereo camera sees almost exactly what we as humans see when we look out the window. And what we can generate is actually virtual views from above. So you see there are objects here. You see the extent of objects fairly precisely, and we can color code the motion, so we see there's two cars here, one is moving, one is not moving. But you see moving means in world coordinates. If you look at the input video, everything moves right here. Even the standing cars relative to the camera, things move, but I can subtract the ego motion and I can get estimates that basically tell me. We even have a quantitative evaluation that says green means 0 kilometers an hour and this red color means 36 kilometers an hour. I'm not sure to what extent these estimates are accurate, but I think they're fairly accurate. What, of course, you don't see the fronts of the cars. We don't, we only see whatever the cameras see. of course. And you see, we don't have reliable stereo estimates, depth estimates everywhere. For example, the ground plane often has very few points only. And that's because it has constant color, gray, so it's very hard to pick up. And so actually, to estimate the ground plane is one of the major challenges, surprisingly, in this setting, because it has very little textural variation. So wherever there are stripes, you actually get most depth estimates. But what you can imagine is that these kinds of results are quite useful to do driver assistance, to now tell you, are there obstacles in the driving corridor? And if there are, this is in the driving corridor, are they moving at my speed or at a lower speed, or are they not moving at all? And so the question whether there is an obstacle is not the only relevant question. The other one is, does it move? So any obstacle avoidance needs to take into account the motion of objects, to make predictions about what's happening, about is this pedestrian going to run into my car or not at the speed he or she is going. And so these kinds of estimates are vital for deciding what to do. Should I keep driving? Should I brake? Or should I maybe try to avoid the obstacle? If I see which way it's moving, I might be able to predict the motion and avoid this. We never went as far as actually doing obstacle avoidance. Our colleagues at Daimler did. At some point it becomes a very important legal question, of course, because you know, depending on what the algorithm decides to do, there are all sorts of consequences. And you can imagine traffic scenarios where you have a choice between 3 suboptimal solutions. You know, one is to hit the child, one is to hit the truck, one is to hit the lantern post. You know, sometimes if you're driving at a certain speed, you know, the car knows, you know, how fast it can brake. So we have an estimate of how long would it take to stand still. And then we can see at the speed we're going, we are definitely going to hit something. The question is what? And that's a difficult decision, right? And if you decide for the lantern post and then it turns out it wasn't a lantern post, there was a person standing there, that's not good. Or if you decide, oh, let's avoid the dog in front of the car, right? Maybe a dog is running on the street, so you veer out to the other lane and then there's a truck coming and it kills you, then you save the dog, right? Yeah, but you know. So there is very difficult kind of decision-making processes that follow here. Ideally, you know, we'll never face a scenario like that, but of course it can happen. And then the question is what to do, and the next question is what are the legal consequences? Whose fault is it? And this is very difficult, of course, right? In an active, you know, a collision avoidance system, if the car actually actively decides to do things, then it does take responsibility. And then the company is liable, and that's not good. And so most collision avoidance and driver assistance systems are not active in the sense that in the end it's still the user who decides. For example, there are systems that can park your car fully automatically. The only thing that you still need to do is you apply the gas pedal. Why? Because then it's your responsibility. You're applying the gas. All the car does is steer. You know, in principle, the car could also do the gas pedal and the brake. There is a reason why it doesn't. It's because you should still be the responsible. Similarly here, you know, in this scenario, there may be warning signals that are being sent out to the driver telling him or her, look, there's an obstacle, you got to do something. But the problem with that is that the human processing takes a certain time. So if you send out a warning signal now, the driver may only react in a second or two, and that may be too late already. And so there is quite a need for technology in this domain to minimize accidents, etc. But the issue is that it's not so easy, partially for data processing challenges and computer vision challenges, but partially for actually for legal reasons. Maybe one last comment to finish the optical flow and correspondence chapter today. We actually published this in a book that appeared in Springer together with my former PhD student Andreas Wedel, who is now working at Daimler. We published this in a book called Stereo Scene Flow for 3D Motion Analysis, and it contains a lot of the technicalities and details on how to implement this, etc. So that's all. Thank you very much.